Okay, welcome to the next podcast. I took a pause on this particular subject because my people discovered something in I'm going to show you just a little bit of it now, and I'll just say it's the flux capacitor portion of the magic wand. Um, there's a couple other components that are still due to eliminate what I'm about to show you. We're referring to that, and that was uh, developed by Sonia as the pixie dust. So, and you'll see why I'm calling it that. There are uses for the technology I'm going to show you. I just finished writing a paper, which I used it. Actually, I wrote two. One was an IEEE paper, in which we were looking at that. The other one was something that just happened to happen yesterday before I drove back from, well, I mean, 2 days ago, I should say, before I drove back from Oklahoma. In any case, we're going to take a look at that right now. And I'm going to switch over to the recording at a drill press. Now, it's going to be a single phase motor. We are using the Empower system. Single phase motors can be used in electrical signature analysis just like anything else. So we're going to take a quick look at that right now. Okay, for this step, I am going to do this all by hand. Yeah, that's a single phase motor, but the Empower and the Empath will do single phase motors too, but in particular, it's a roll steel frame for the second part of this. We're going to, basically what I want to do is see how our magic wand, powered by pixie dust and detected with the flux capacitor works. We're going to have a little fun, basically. I'm going to show you some other stuff when we're doing the other part of the discussion, having to do with something cool I did. Actually, I'll show you real quick. What I had to do with the machine in one of the papers I wrote was literally just go bonk, hold this up against the side of the machine. You know what? If we get a chance, we'll do that here as well. Just so you can see now, and then we're going to discuss what we're actually seeing. People keep talking about it as stray flux and all this other crap. It's not. I don't know how it's going to turn out on this because it is a grounded machine. I don't know how much noise is on here. I don't have LEDs. They're T5s, but they're still electronic ballasts, things like that. So there will be some effect. So let's go ahead, and it's going to be noisy, so I'm not going to talk too much. We'll turn on the drill press, so it's running. I've already entered in the nameplate information. So let's see what it looks like. Get rid of that background stuff there. Let's get this background stuff up, and then I can. There we go. Let's go ahead and run that analysis. Okay, so we'll wait for it to settle. Peak current is right around 10 amps. There's not drilling anything, so it's just a single phase motor. Let's go ahead and collect data on this. Then what I'm going to do is I am going to pause what we're doing because there's no point in everybody watching this collect data for 120 seconds. So bear with me. Okay, so just a second, we'll see the data pop up. I put in an estimated data because there's no nameplate on that little electric motor. I'm assuming because of what was on the tag for this drill press that it's a half horsepower. No guarantee on the speed, but we'll know that soon enough. Now, I have everything turned off in here except the pulleys and shifts. That data I can get later. I mean, we've got good information here. You can see the hump there in the middle. That's actually going to turn out to be static eccentricity, or yeah, probably static. There's a few things going on. So let's go ahead now, and for fun, I'm going to run another analysis, except this time I'm going to hold that current clamp up against the side of the motor. Okay, so watch things settle. Sorry about that. A lot of junk back here. So as you can see, I'm just holding this up against the side of the machine, and you can see that there. For fun, I'm going to go ahead and pause, and I'm going to select data collection. So that, right there, is going to be our second set of data. And I'm going to pause again until this gets through this, and then we'll see what that looks like compared to the first one. Okay, it's running. I haven't blanked out the old data, so it's still sitting there while it's running. You'll see that all be replaced here shortly with whatever it sees. So right now you can see the peaks of that. So there it is. It's pulled up the right stuff. You see some of my peaks are still there. I'll explain what that is as we get into the rest of this presentation. Now let's go ahead and we're going to take our device that I had made for me. This is the nose end of the magic wand, and we are going to put it, attach it as a magnet there. Now I have to do a couple of things. I'll show you. Well, I have to connect the device down to there, and the jumpers didn't arrive that I ordered, so I'm going to have to hold the laptop up. But I will show you what this data looks like in just a moment. Okay, for this one, I went ahead and just boosted it up a little bit so we can get it there. That's the nose of the magic wand. And no, it's well, I jokingly call it a flux capacitor. There's really, well, like I said, I'll explain it when we go back in. Let's go ahead and see what this looks like. Haven't tried it yet, so there we go. Much more solid based on how I have it designed than holding the current clamp up. Not close to what the actual current is, of course, but then again, I haven't entered in any type of millivolt per amp rating for this, so I can do that right now. So let's go ahead and change that so we get it close to the other. So we'll set this to 500. Okay, and we're going to save this, but we're going to say magic wand. We still have a few other things to add to it that we will be calling pixie dust. But right there is a flux, and we're calling it the flux capacitor and the inductive capacitor. In any case, let's go ahead and let's take a look again what it now looks like. See if it's, oh, I went the wrong direction. So let me cancel that. I keep forgetting you have to go the other way around. So let's go back to these settings, and we were at 10, so we're going to call that 5. And save it. If not, I can mess with that after. It's not that big a deal. Let's see where we are. It's a little too high. So, got the rough idea. So it's telling me 30 amps peak, and it's all over the place. Well, there's reasons for that too. Let's go ahead and, so we're at 1. Okay, so I'm just going to change this back right now to, let's call it 50. Basically, I still have to calibrate it, but let's see what the waveform looks like. Because there's not that much current sitting on the surface. The idea is to try to see if we can get something that approximates the other current. Whoops. Okay, let me figure out why it locked up. There we go. I just didn't like some of the noise. Anyways, I'm not going to mess with it anymore. We're going to go ahead and just collect the data. And while it's selecting that third spot. I'll put this in the video on pause, and then we'll see what that waveform looks like. Okay, so we're about to get to that point now. Just save the data. You can see all the crap running in the background. So let's see how that compares to this one and the original one. And then we're going to look at it on the screen as I walk through what we're actually seeing. And, you know, for those academic watching, yeah, this is going to explain what you're actually seeing versus what you think you're seeing. And look at that. Woo! Yeah, see all kinds of different noise. Well, why on earth is that? That's what we're going to talk about. Okay, so let's go ahead and open up that data, the first ones. I did an extra set after that I'll show you, so everything is continuous. So we're going to go ahead and open up that data. And we're going to take the first one taken here. That's the date and time. And then, of course, the drill press. I'm going to open that up. Now, as you'll see, this is a specific waveform. This is the one that was taken directly from the machine. Then I'm going to do something else you haven't seen yet with the Empower. Now, I'm assuming the machine is 2-pole, but we're going to take a look at this. I might have to adjust the nameplate just a little bit. Could be at 1800 RPM, but there is no nameplate on that motor. Took the cover off, and there's not one inside either. I just know it's a 0.5 horsepower. Okay, we're almost there. Okay, because I'm running everything, it's going, we're going to be slow. Okay, so here's my information. So there would be a peak at about 120 hertz, which is right there. There's a double peak. That's indicating it probably is 3600. The other thing is there is also a peak right about just under 90 hertz, which could also be running speed. So, but then I've got these peaks out here based upon what's probably 28 rotor bars. So, tough one, because I have the peaks for it, but I also have a belt and shiv in there that I don't know what those speeds are. I suspect this and this are belt speeds. Or something with the shiv, so or even the output speed. So let's go ahead, because the machine will go up to 3600 RPM. The pulley size varies so that you can adjust it around till you get to that. So it's possible it might double speed. So I am going to. It says 3600. So I'm going to assume it's an 1800 RPM. So let's call it, just for fun, we're going to call it a 1735. I'm going to change that nameplate. I can always go back later, but 1735, and we'll save that information. And then I'll do the same thing when we do the other. Okay. All that in the background is just this. So I'll go ahead and auto-analyze this one. Let it see what it thinks the speed is. Now, it wasn't heavily loaded, so 6.9 amps from the higher one. That particular crest factor, 10.89. Okay, so let's see what that is. 10.89 divided by 6.92. Crest factor 1.5. So there are harmonics present, by the way. That's very interesting. So we're going to go take a look at that. Now, this is a clean machine. I'm running basically a single-phase motor, no electronics associated with it. But the outlets there are fed immediately from the incoming main to the building. This location of ours has got 120 volts coming in. So 120, I think, yeah, just straight 120. So my panel is straight 120. The air conditioning units, including one brand new premium efficient air conditioning unit we put over my office, that one has electronics in it. The other one was relatively new. I hadn't taken a look at that one, but I saw the one as I installed it. So there's a little drive on it, rather complex, cool-looking control. Hey, only the best for my office, right? So in any case, so this is the lab, and we've got certain things here, and I do have power harmonics. Plus, I've got a neighbor on one side that does all digital stuff, including having servers. And I've got a neighbor immediately on the other side that's an environmental laboratory, and I can smell them running stuff today. Okay, so let's see. Unbalance or misalignment, that makes sense. Rotor bars, let's take a quick look and see what it selected at speed. So relatively high speed. Let's see if we got the rotor bars. Yeah, tiny little peaks. So with adjustment still, that's definitely going to be casting voids. If you've listened to my stuff before, casting voids mean what? Well, the motor's running fine. Don't worry about it. So I have all these other peaks, most of it associated with the different components in the drill press. Let's take a quick look at what the waveform actually looks like. I mean, I could do that here. Let's do that. No, it's too tiny. Let's go and do a harmonic evaluation. We're going to look at this strictly in dB, and I'm going to do this again on the next one. And it should pop up any hour now. Here we go. Okay, you can see it's not on a VFD because all my harmonic content sits right back here and dies off, and it's at 100 dB down, so that's really good. On a VFD, it's going to be sitting up here somewhere. So let's get in closer and see what this looks like. And there's what we're looking at right now. Okay, so we've got that. Let's take a look and see what the actual waveform looks like. Okay, and let's get in and take a look at that. Okay, sharp peaks, and then finally, let's take a look at the actual harmonic content itself. Now I'm going to keep these up here. I'm going to run a second instance of the Empower, so we can do a direct comparison on what happened when I put the CT against the side of the motor. Okay. Here we go. That's interesting. Let's take a quick look down here. So I have some pretty good third harmonic, about 2.5%. Now, I shouldn't say horrible at all. Teeny bits of fifth and seventh down there. How about that? So 2.83% total harmonic distortion in odd. Really nothing super harmonics, which we didn't see. We would have seen back there under that. So let's go ahead, and what we're going to do right now is something I haven't shown. I don't think I've shown people before, but something this very well does. And let's take a look at something here. So I'm going to check the condition of the bearings, outer race of the drive NE. Okay, that all looks good. So we've got this here, and I'm going to put these on this side. And let's go ahead, and we are going to run another instance of Empower, because I want to be able to show you what's going on. So let's minimize this one. I'm going to minimize this one, get rid of the background. This will take a few seconds. I'm going to go ahead and pause. Okay, so hopefully I don't start lagging too much for overburdening the PC, but as you can see, I've got now a second instance. So let's go ahead and open up the one where I put the CT against the side. That'll be the second one. And we'll take the normal thing there. You're going to see about 0.1 amps. This is important, very important for what I'll show you next after this. Okay, now this was just holding the current clamp up against the side. You can see I'm about 1/10 of the actual current. It does not look the same. You can see that. So the waveforms there. There's no difference in how I took this data. And I'll explain what this is as we go further. But let's take a look at where we are here. You can see I have a slightly raised noise floor that has to do with all the belt stuff and everything else. Some of the signatures appear to be the same, but you can see they're a much lower value, and I've got a much higher raised noise floor. There's also other things popping up here. So let's go ahead and we'll run that auto analyze. But you know, I mean, technically, if I were to just pick this up and look at it, and I'd go, okay, it looks similar, but this very high raised noise floor, that is something specific. Now we're going to go ahead and run that, so I'll show you what it picks up and thinks the speed is. There should be no change in speed. Okay, so without doing anything, just letting it run. So I've got 1787.54. That's the accurate speed from a direct current signature analysis measurement. This is from what's sitting on the surface just from placing the CT against the side. My levels are lower, but as you can see, I've got a lot of other things it says it's seeing. Okay, so both bearings bad, all this other stuff. And this is with the adjustment for that raised noise floor. Okay, so it thinks it sees a bunch of other stuff going on, and as a matter of fact, there are peaks associated with those, and it's the right speed. So do I actually have a problem? Well, no, those bearings are not showing a significant issue here. They're falling off to one side. So the noise alone from here is doing that. So I've got 1, 2, 3 false positives out of 5 findings. I am aware of this because I have inspected this motor. Okay, so so I've got 3 false positives there. Let's go ahead and do one more comparison. This time we're going to take basically it's a specially built device. It's basically a coil. So we're inducing into it. There's more to it than that, and there's some components not on it yet. But I would get the same thing if I put a different style of coil on there and did the same thing. And I know why it's occurred as to what we're going to see. So let's go ahead and we're going to run oh, let me see something. I meant to do this. I need to run the harmonics. So we'll pause while that's going on. Okay, so I'm now replicating what we had on the others. So let's go ahead and take a look here versus here, okay, you can see similar but very dampened. So I've got a raised noise floor, so I've got a lot of noise, and it's shutting that down. Well, where's that noise coming from? Well, that noise is some additional harmonics. So you can see that my harmonics from a direct measurement are there, and here they're much higher. What on earth happened? Well, let's just say I have lighting systems through a concrete barrier, that back wall. I know they have some electronic machinery, and then we have some other things going on, including looks like the transformer serving us may be a little overloaded because I've got some even harmonics. The surface of an electric motor is a great antenna. So that means that steel, that rolled steel that's there, is picking up the electromagnetic induction, the fields from everywhere else, including ground. So we're going to talk about that in a couple of minutes as well. So there we are. So now on top of everything else, I have supraharmonics. And let's finally take a look at the straight coil, which means it's going to pick up everything. There's some things I left out, so it's also going to pick up even more from the surrounding. And I do know what they're running next door, so I'm expecting not to see my primary frequency at 60 hertz, which is really possible, especially seeing if it's inducing through the wall into my sensor. Then we'll start talking about what people think they're seeing with these Flux devices. So hold on. Actually, while we're waiting for that to open, I meant to look at this. So it's working in the background. It's a little slow because I'm, as we've talked about before, I'm tying up a lot of things, so my voice is probably lagging behind what I'm saying. Let's take a look at this waveform. I meant to do that. You can see all of this extra stuff sitting in there. Now this is just the current clamp. So this is all sitting, and it's all of the noise from around that area being picked up by the frame of the machine. So I'm getting I've got 3 now false positives using just a quick test because of irradiated fields from everything surrounding it, because my lighting, my electronics, wires in the wall, everything on ground, everything is emitting. And all your metal surfaces are going to pick up that stuff. So let's go ahead and see what happens when I put we'll just call it the flux capacitor, because it's missing the other components and make it a magic wand. And basically what we're doing with that is focusing in, so we're just collecting off the surface of the machine right in that spot. If it works, it's going to be a leap forward in flux analysis off of an electric machine, and not from the stator. We're not reading anything from the winding. So let's go ahead and open the analysis. This will be the third one. So now I've got 3 instances of the software running. Yep, you can do this. Gives you the ability to do comparisons. We've got more stuff coming, folks, in the Empower that'll knock your socks off. You know what? I'm not going to select the Magic Wand one. We're going to select the same one so that everything is identical. No difference whatsoever. I'm not going to have tried to adjust anything or anything else. So when I videoed it, I had tried to fool around with the numbers, and I saved that Magic Wand bit. So we're going to apples to apples to apples. And I'm going to pause while we're waiting. Okay, so with the device that I've now attached onto the side that is going to measure basically everything else, and the way it's configured right now, because I haven't added the other components, it actually adds to the antenna effect of the surface. So just putting a coil up against the side of the machine, basically, this is a coil with some stuff around it that does certain things, and basically is meant to emphasize the very, very low current flow on the surface, which, as we can see from the current clamp, is roughly about 1/10 of an amp. So, or actually we'll know in the next test, because I switched everything off and I did an extra test, and I'm going to keep this rolling and I'm going to show you what that is. So here we go. And just to put this into perspective, here is what it looked like with the current clamp, and here's our direct measurement. This is true measurement of what's going on in the magnetic field of the machine. So this is a much higher current, so it's drowning everything else out. So here we go. Let's go ahead, and we are going to let it analyze itself. And well, it does that. Well, we'll just keep live. So basically what's happening in what people think are these flux things, because an electric machine has to meet certain emission standards for induced magnetic fields, EMI. It's not supposed to be inducing into other pieces of equipment nearby. Lighting and everything else is supposed to have limits on it, but an electric motor very specifically has a number of IEEE, IEC, and other standards that are required in order for it to get a CE stamp on it, let alone a few other things. So this mound here that we see, all of that is additional noise. We can see this came down a little bit because now I can pull up some of the other stuff, but all these peaks have nothing to do with what's coming off the motor. Let's see what it thinks it sees now as far as an analysis goes. And, whatever's next door, lighting systems, air conditioning if it's switched on, all that stuff is inducing, and every surface of your machines pick that up. We ran into this when somebody had put one of these devices on a machine. It was costing a company a ton of money because it was a critical machine, and they thought it was the motor that they were looking at. In reality, it was another machine, another motor, a little ways away, and the what they were really seeing was the ground currents from that motor that were feeding into ground, and then through the ground leads to the other motors nearby, feeding back up into it, and then causing, basically current flow on the surface of the machine. You're going to see us talking about this more and more as we do these studies we've been involved in, having to do with why we're suddenly seeing a rapid increase in shaft current failures, bearing failures due to shaft currents. They're not always shaft currents. Sometimes it's surface currents, and I just wrote an article about that. But especially as companies begin to roll out more and more electronic systems, energy-efficient electronics-based systems, and everything else, without doing simple filtering and so on and so on and so on. So if I put in, and I have a really nasty, dirty ground because some marketing guy had sold me that their drive is clean and meets IEEE 519, read my article on that lie, that kind of thing. 519 is not meant for specifying an inverter, let alone a branch in your system. It's only meant for between you and the utility at the point of common connection there. I'm going to pause this because, here it goes. So here we go again. So it actually picked up a speed that is relatively close to the others. Does that mean that I've got a problem with anything? I'll know. So 1777, so it's off by about 10 RPM. Doesn't surprise me because there may be something else that's doing that, or the raised noise floor may cause that. But here we go again. It's telling me I've got a DE bearing, ODE bearing, and winding stress, so I'm back to 3 false positives. 3 things that don't exist. I've already checked it. I've done vibration on this thing. I've done this on this thing. So basically, every time I have a motor anywhere near me, it's getting tested, no matter how small it is, just to play with devices. So right now, there's where we are. So let's go ahead and I'll show you what I did next. So this is the part I'm doing separately so you can see what I just told you. And I've got the current clamp set on ground. All the settings are exactly the same. We're going to go ahead and start up the machine. Okay. And we're going to see what the ground looks like here. Okay. You see that I'm seeing ground currents very similar to the other. Okay. So let's go ahead and we're going to collect this data. That'll be the fourth set of data that you would have seen on the screen that I was discussing what we're actually looking at. Well, what are we seeing here? Now, this is just from here. It doesn't include anything else. And you can see that's not particularly clean, even though I'm coming off a straight 120 hertz. There's a couple of things that are occurring. One is harmonics in the machine, leakage current to ground, and then, of course, whatever is nasty in my incoming power. So whatever harmonics are present, because this is reading directly off of my supply power, which goes outside to the transformer. Okay, so now back to the regularly scheduled program. So as you can see, I fooled you just a little bit, and here's what we're going to look at there. So I'm going to open up yet another instance of Empower. Keep these in mind just in case we need to look at them. But let's take, that's something I didn't do. Let's go ahead back here with all this nastiness. I should have done this. Let's take a look at the harmonics, and then we're going to take a look at the waveform as well. Apologize for that little bump in the road. Okay, so here's our spectral analysis. Let's take a look at what the current waveform looks like with this new stuff. Okay, you can see much nastier looking. So let's zoom in and we'll just pick a random spot. Okay, rounded off, other things going on, lumps and bumps, and those are all harmonics basically. So let's take a look at the harmonic values, and then we're going to open up the other one and close out all the other ones so you can see what. Oh, no, I got to leave it open, don't I? Let's go ahead and start up another instance of Empower. I'm going to pause while we're waiting. Okay, so here is the harmonics for this one. You can see, not really kind of see that I'm looking at something a bit different now. So let's come up here. Now I've got a high even harmonic, and then third, fourth, fifth, etc. So I have this odd, weird second harmonic that's come up. So that's going to add even more, and then I have so 16% even harmonics. Where's that coming from? Well, who knows? Because I'm basically now picking up everything radiating around me. So at some of the trade shows, I picked up some of these flux, stray flux things, and I look at them, and I tell you what, this is the kind of crap they're actually picking up on. They don't have certain features in place that you require to not see this. But now let's finally take a look at ground, which is going to show yet again something probably even more different as well. So everything's starting to open up here. It'll take a few seconds, a few minutes, and then we'll see what the ground looks like on the machine, and then also the harmonics for that. Just to give you an idea of all these different things we're seeing that are going on in space around a machine that I don't have like heavy machinery sitting right next to us. I don't have a VFD radiating like crazy right next to it, or shoving stuff in the ground. Matter of fact, it's the weekend, so the only thing I have on inside the building is, well, the air conditioning and heating. I've got it set at heat, and it's 68 degrees outside, so all I have is the lighting. It's the only load we have today, so let's see what that looks like. Almost there. I'm watching it running in the background here. There we go. So that's an actual ground reading taken from where I was showing you. Now this noise is even higher. This looks just like what I took with the current clamp. Very, very low current on ground. Those are losses, so those are going to be related to that. So let's go ahead and see what this one tells me. So we'll click that to run its analysis. I've got this oscillating bit of current here too, and chances are that either has to do, probably not having to do with the capacitor, probably more so has to do with the rotor. We're almost there. It's running all the cursors and all its findings. Now, in some big machines, I've had to take measurements off of current and so on to see what it looks like. Then I'm going to open up a set of data I took at a location and show you what we saw there. I'm going to shut all this stuff down, of course, except for one, so I don't have to wait to open it. So that'll be machine in an actual operating plant, and that goes along with that one article. I did basically the current clamp held against the side of the machine because there was no ground lead, and that's really what I was looking at the motor. The ground lead was in conduit back to the drive, which was the actual problem that they were running into. Almost there. Things are slowing down the more I have open on the computer. Hopefully all these recordings are doing what they're supposed to do. Here we go. Oh my gosh, I've had yet another one. So now apparently in addition to what I actually have, I now have a stator slot defect and a dynamic eccentricity. So now I have 1, 2, 3, 4, 5 false positives off of ground, but this signature looks a lot closer to, and it's also close to the original speed. So I'm getting better data off of this. Very high raised noise floor. The alarm settings are where they need to be. Yeah, so they're not overly sensitive. Let's go ahead and take a look at the harmonic content here. So now this would be the ground at the motor itself. So question is, what does that look like? Okay, and here we start. Okay, everything's in a little bit tighter. Let's take a look and see what the waveform looks like. Okay, here's our waveform. Let's jump in here and take a slice. Okay, so very pixelated in here, but obviously a lot of noise. So let's go ahead and open up the final step, the harmonic analysis, and see what the harmonics look like. Very, very low values, so that's why it's pixelating, because Numbers are so tremendously tiny. And it appears that we are back pretty much to the beginning. So third harmonic, lower everything else, almost non-existent even harmonics, a little bit of fifth and seventh, stuff like that. So basically, there you have it. So if I'm taking data on a machine and I want accuracy, that data has to come directly from the current. If I take off the surface, I'm going to detect all kinds of other stuff going on in my ground system, all that noise and everything else. So let's go ahead and we're going to shut down all but the first one. Funny part is if I shut down the main, I can still keep up those other spectra. So let's go ahead and take a look at a real live machine. 5 horsepower, not a big one. I do have a big one too, but that's for another day. So let's take a look here. So open analysis, let's go find it. Because of certain things, let me pause. Okay, so I'm opening up this data on a 5 horsepower motor. It's a cast iron frame. They've got a high voltage, high shaft voltage, or going through bearings and stuff like that. We'll open this one up and take a peek at it. Then I've got to go back and see if all the videos that I've just taken for this session are still present. I paid a lot to upgrade to this version of the recording software, and for some reason, higher cost, more SaaS, worse ability. We'll just put it that way. So let me wait. Let me hold on here, and I'll be right. Okay, so here we go. A small motor, 5 horsepower. A common brand. This is all the nameplate information here. We knew the bearings, the rotor bars and stator slots, and there's everything else. The analysis is pretty straightforward. You see this big lump here. I'm not going to worry about that right now. We're just going to go ahead and open. We're just going to go ahead and open the other data. But what I want to do first is let's go ahead and take a quick look at the harmonic content on this one. Then I'm going to just open up the next component off this. So the next one we'll do is we'll open what I was doing with the putting the current clamp against the side of the machine. So this is what commonly looks like on the output of a VFD out to 22 kilohertz. You can see these are a combination of harmonics, even and odd harmonics, all the way out to, this is 22 kilohertz out here, and the relative force decibels pretty high comparatively all the way out, and it would go further if I read further out. The waveform looks kind of like this. Now this is on the output side of a double filter system they put in. So they had one filter in, they were having problems, so they put a second filter in. It still looks nasty, and what's the reason why? Well, just to shorten up the discussion, they ran a ground lead inside the conduit with 3 loose power leads for about 4 meters. So you've got 4 meters or 12 feet of basically 3 power leads inducing into the current. So all of this is then transferring to the surface of the machine. So it's telling me I've got, with that signature, that I have very low harmonics and current. Okay, which is good. So let's go ahead, and I'm going to close out of these. Let's see what it looks like. On the with the current clamp on the surface. And we'll pause. Okay, so here we go. It looks very similar to what we just read, and it is. I've got a slightly high raised noise floor with all the noise from that because I've got all the resistances and everything else across the surface. I've got any losses from the current clamp and the distance, things like that. So, you know, that's part of what I see. The further you get that current sensor away from the surface of the machine, where the actual surface currents, not flux from the winding or flux from the air gap or flux from the core, sorry, that motor's in a Faraday cage. You're reading off the surface on the outside of the Faraday cage. So you're not reading the same thing. You are reading basically noisy filtered data. And then let's see what that noisy filtered data looks like still. So as you can see, all that noise is still there. It's just got, you know, the harmonic content's still there. It's just got noise masking most of it. So I'm not going to go into the rest of that part. Let's finally look at ground on the machine. Now, this is a direct measurement off the ground coming back from the motor, and includes and going straight to the VFD, the common point. So let's. I'm going to go ahead and pause and open the data, and then I'll show you. Okay, so the ground lead, on the other hand, this is what it looks like. Some additional noise looks closer to what is on the machine. Well, that's because all of the ground noise of a relatively low current is being induced into it. Now, mind you, the motor itself is only drawing about 2 to 3 amps, so this is actually a fair amount of current for that. But it's feeding right back, and that's what the drive is referencing. Let's take a look and see what the harmonics look like. So all that current and any voltage that's being induced as well is sitting on the surface of the machine. So where they thought they might have had 60 volts on the shaft reference to the frame of the motor, it's very possible that it's it's the opposite. So here's that same set of harmonics there. So as you can see, this allowed me to troubleshoot certain things. Do I trust this data? Does this compare to the other one that we did? No, there's extra peaks in here and everything else from other things in the area, including another machine running right next to it that's radiating off its surface, lighting systems, HVAC systems, all kinds of moving components, all of which are causing the surface of the machine to have an antenna effect. So the ground, yeah, it's somewhat close because, and I shouldn't see this on there, I should see a dampened version, just like you saw with the one back here. But I'm running loose conductors inside conduit. I should be expecting things to go wonky. And with that, have a great day. I hope this was educational. If you have any questions, please feel free to reach out to me.